So let's begin part two of the video with a quick summary of the things that happened in part one. Exercise one was more straightforward, where I gave you the point and asked you to find the tangent line. Exercise two, in a sense, was backwards because I was giving you some information about the tangent line, the fact that it was horizontal, and then I was asking you to find the point where that tangent needed to be. Exercise three was kind of the same thing. The information that was given in that case was not about the tangent line, it was about the normal line, but that's not what makes the difference. The difference is that you had to be comfortable working with a letter P instead of with a number 2 for a longer number of steps before you got to an equation that you could then solve to find the value of P. So here's problem number 4. It is the same function and the same point as what we had in the previous one, but now he is not asking anything about distance, so we are not going to want to talk about normal lines. Instead, what he is asking is for tangent lines to this function that pass through this point. And although this is not a particularly long question, it has very few words, so it should be straightforward. But still, there are two comments that I want to make about just the reading of the question, which are two things that I often see people get confused with in this kind of question. And before you say that this is a language issue because I am teaching in English, that is not the case. I've seen the same two confusions when I'm teaching this in Portuguese to Brazilians as well, okay? So it's not a language issue, it is a math issue. The first one is that this function does not pass through this point. 2 is not a point in the curve y equals x squared because 2 squared is not 2, it's 4. And people get confused with seeing the sequence of words y equals x squared passes through the point 2, 2. But that is not what is written there. So when the verb is to pass through this point, the subject attached to this verb is not this function. It's the tangent lines. The tangent lines pass through this point. That is the sentence structure. It's subject, verb, object. The subject is the tangent line, the verb is to pass, and the object is the point that they pass through. And the second one is that the word lines is plural. It's not just find the line, it's find the lines. So that's a hint that you're going to have more than one answer. And if you look at the picture, you can begin to visualize where both of them are going to be. The sentence is not really hinting at the fact that it's exactly 2, but it does hint that it's more than one. And I'm telling you it's 2, so you can visualize it. And the other thing is that the word lines is plural. The verb is also plural because if it was singular, it would be the line passes. It wouldn't be the lines pass. But that's not where most people get confused. They get confused at the word any because any, to some people, sounds singular. Find any one of them if there are multiple ones. And that's not what it means. Find any lines means find all of them. Any that exist, you have to find. So you have to find all of them, okay? So my green pen is not working very well, but hopefully you can see what I've sketched here. It's both of the solutions, okay? There's going to be one line that passes through the point and is tangent to the curve up here. And then there's another one with a smaller slope, but still positive, that touches the function here. So I'm going to do pretty much the same thing as I did in the previous one. The function is x squared, the derivative is 2x. Then I'm switching between talking about x or p for the same reasons that I described before, because x is the independent variable and p is the x coordinate of the points that I am looking for, which are the two green points. And then I want to write down the tangent line. The slope of the tangent line at p is 2p. The rest is just y equals ax plus b, which is just the equation of a straight line. And now I need to substitute a point from the line into this equation in order to find the value of b. The point of the line that I know is the point 2, 2 that the tangent line must pass through. So let's plug that in. So this is the value of b that we find. to put into the equation of the tangent line. Now let's move that up here to keep going and try to find the values of p. All of those lines, regardless of the value of p, they pass through the point 2, 2, because this line was built intentionally to make that so. But it's not true that for any value of p, what you get here is a line that is tangent to the function. You can try random numbers to check that if you want to, but trust me, that would be too lucky. Instead, in order to make this into a tangent line for that function, you need very well chosen values of p. So you are going to have a green point, which is p and p squared. Those are x and y coordinates of that point. So you need to put p squared and p here in order to make that work. So that's the substitution. X is p, y is p squared. You can see that there's another p squared appearing here, so that's going to simplify the equation. So in the next two lines, I'm just organizing it a little bit. It turns into a quadratic equation that I don't want to factor because the answers are not easy numbers. So I've plugged everything into the quadratic formula. And this can be simplified a little bit. 16 minus 8 is 8. 8 is the same as 2 square root of 2. And now I can divide everything by 2. There you go. That's two different answers like we expected to find. The x-coordinate of that point there must be the 2 plus root 2 because it's the bigger of the two. And this other one must be the 2 minus root 2, which is smaller, but still a positive number because the square root of 2 is not as big as 2. Okay, so technically we didn't find the tangent lines yet, which was what the question was asking us to do. Instead, we've just found the values of the points in the function where the tangent lines are going to do where it wants to do. But then I'm not going to do the rest because the rest is easier. We just take the values of p and plug it here, each one separately, and then you're going to get the two equations of the two lines. Problem 5 is this one. It comes with this picture. It comes with the coordinates of this point and this point, which are 0, 2, and 2, 0. It tells us two functions which have four unknown values, p, q, r, s, which they want us to find. And it also tells us that this line that we see in the picture is tangent to both of the functions in both of those points. So the first time you see this problem, it can be a little bit surprising because it feels like he's not giving you enough information for the amount of things that he's asking you to do. He's asking you for four things, and it looks like he's only giving you one thing, which is this tangent line. But then when you start to think about it, it's not just one tangent line. It's actually two tangent lines because he's telling you that it's tangent here and tangent there. So that's already two pieces of information. And actually, each tangent line has a slope and an intercept. So that's actually four things. But we don't have to think about it in this way right now because we have a lot more concrete information about this line. This is a line that passes through the points 0, 2, and 2, 0. We know exactly what the equation of this line is. We know that the slope is -1. We know that f is the blue function and g is the red function due to the fact that f has concavity down and g has concavity up. So we know that this slope of -1 that we were just talking about is f prime of 0 because x equals 0 is where the line is tangent to f. And at the same time, it is g prime of 2 because x equals 2 is the point where the line is tangent to g. So that's where g is supposed to have derivative -1 because the slope of the tangent line at that point is known to be -1. So at this point, you can just write down both derivatives of both of the functions because they are quadratic functions. They're easy to take derivative of. And then you can plug in x equals 0 for f prime and x equals 2 for g prime. You know that both of these numbers need to be equal to -1. Well, this is 0. And this is 4. So I already know two of the four letters that I wanted to find. I know that P is -1 and R is -5. I'm going to put that up there. Okay, so I guess we've already done everything that we needed to do about the slope of the line. And now we can just think about where the line is passing through, what the point is. So it's the point 0, 2, which means that f of 0 is equal to 2, which in turn means that q is equal to 2 because you can just plug in x equals 0 here. And we also know that g of 2 is equal to 0. So I can just plug in the x equals 2 into that formula up there. And s equals 6 is the final piece of the puzzle that I was looking for. Exercise 6 is also about two functions having a common tangent. This means that it's one line that is tangent to both functions at the same time. In this way, it's similar to the previous exercise that we were just doing, but now he wants that common tangent to be at a point x equals p. And that is not what was happening in exercise 5, where the line was tangent to both functions but at different points. And now we want the same tangent to both functions at the same point. This is something that's going to look like this, okay? It's two functions that are tangent to each other, which means that if you take the tangent line of one of the functions at that point and the tangent line to the other function at the same point, that's going to be the same line. We don't know what the point is. The question is just calling it p, but we're probably going to find that out. And of course, the functions in this example don't look like this, okay? They are quadratic functions. So I'm going to erase this picture and draw a nicer one. Okay, so that's f. We know every single thing about f. We have its full expression. It is a quadratic with concavity down. The zeros are 0 and -1. And g is given in its vertex form. So we know that the x-coordinate of the vertex is 1. And we don't know the y-coordinate of the vertex. In fact, that's exactly what we're trying to find. We're trying to find k. So let's put that in the picture somehow. The vertex of this function is going to have to be somewhere in this dotted vertical line. But I can't just put it anywhere I want, like here, because if I put it here, then this function is not tangent to that function. They don't have a point where they touch. On the other hand, if I put it too far down like this, the functions are going to cross. So they cross at one point and at a second point. That's also not what I want. I want them to touch each other as a tangent. So it's going to be somewhere between these two things that I drew here. So I'm expecting my answer k to be a negative number. And I kind of hope that it doesn't turn out to be that the point where they touch each other is x equals 0, because it's looking like that in the picture that I just drew. But that would be too much of a coincidence, and I don't like it when things like that happen, because it feels like that is a feature of the problem, and that, oh, if functions touch, then they always touch at 0, which is obviously not true. So I don't like it when these nice things happen by coincidence in problems. I don't know if it's going to. I'm just saying. What I'm definitely going to need is the derivatives of both functions, right? So that's the first one. And before I do the second one, I actually want to expand this thing here because I promised in the beginning of the video that the chain rule was not going to be necessary, so I want to keep to my promise. So there you go, g is expanded, g is differentiated, and now what? I clearly want to find a point where both tangents are the same, and in order for that to happen, they do need to have the same slope, right? Because if it's the same line, it's not going to have two different slopes. So I do want to set this equal to that. But it's important to understand that I can only do that because I want the lines to be at the same point, okay? This was not something that was happening in the previous exercise, so I wouldn't have been able to do that there. Because when I put one equal to the other, I'm saying that I'm talking about the same x, the same point. And what is the meaning of the x in this situation? It's the x coordinate of the point where they touch. It's the x coordinate of the point, the same point, where both of these functions have the same slope, which turns out to be a half. That makes me happy because it's not 0. But x equals a half is not the answer to the problem. It's not even the slope of the line. It's just the point where I'm going to find the appropriate slope. And the thing that I want is not even the line. I want the value of k. And here's the reason why these types of problems about common tangents tend to confuse people. It's because a lot of people have it clear in their minds that the same tangent needs to have the same slope, which is what we just did. But for some reason, people tend to forget that the same line also passes through all of the same points. I mean, it is the same line. If same slope was the only thing that you had, you would only actually have parallel lines, not the same line, not a common line. So x equals a half was something that I found from setting f prime equal to g prime. But now I also need f equals g for x equals half, because that is the point where they are tangent. I need f of half equals g of half. And that is what is going to give me the value of k. So I've plugged in a half for both of the functions. And now half squared is a quarter. Half minus 1 is negative half. Negative half squared is also a quarter. So now I'm going to subtract a quarter from both sides here. And it turns out that the answer is that k needs to be equal to negative 1. Picking back up on the list of the problems that we went through and how they are gradually increasing in difficulty, problem number 4 wasn't really that different from problems 3 and 2. You still had some information about the tangent line, which in that case was the fact that it passed through that point, and you wanted to find out what the point was. So in that sense, a backwards problem, just like the other one. The only maybe surprising thing that it added to the previous one was the fact that it had two different solutions. We found two tangent lines. But if you think of it, that could have happened in problem 3 as well. Remember, we didn't quite finish that one because we had a cubic equation to solve. I happen to know that that particular cubic equation only had one solution, but sometimes they have three, right? So that is something that could have happened before. I just wanted to mention that. And problem 5, though, is a little bit different because instead of being one request from the tangent passing through this point and two solutions, in this case, we are having two requests from the tangent line, which is that it needed to be tangent to one function here and to another function there. So we're asking two things. And we also wanted to find the values of more variables, so there were more letters in there. So that is the extra difficulty, that we're working with more variables. But still, it is the fact that we're working with variables and not the fact of derivatives themselves that is adding an extra difficulty to this problem. Problem 6 was kind of the same thing because we wanted the tangent line to be tangent to two functions at the same time. But 6 was a little bit more difficult than 5 due to the fact that in problem 5 we already had the equation of this tangent line from the beginning of the problem. It was the line y equals 2 minus x. And in problem 6 we didn't have the equation of the tangent line. We knew the fact that there was a line which was tangent to both functions at the same time for the same value of x, but we wanted to find what the value of x was, and we also didn't know what the equation of the line was. So it's basically the same problem, but what's varying is the amount of information that we have to begin with. That's what's making the problems more difficult. And problem 7 is going to take that one more step further. This time we're not going to have two functions, but just one function. It's still just one tangent line, but it's going to touch the same function in two different points. We're probably going to want to find out what the points are, but the question from the problem is to find the equation of the tangent line. So we also don't have that from the beginning of the problem, which again was what made problem 5 simpler than 6 and 7. Now for problem 7, it is highly unlikely that we are going to be able to find a concrete answer just by hand because it wasn't intended that way. This is a question that is intended for the use of technology. So if the calculations become difficult, let's not worry about that. What we are focusing on is the structure of solving the problem. So by now, because we've been doing a sequence of exercises, we're not just starting in this one. I hope the fact that it's one line being tangent in two places is not surprising anymore, because we've seen other examples of how this kind of thing can happen. But this is the first time that we're going to want to find 2 points, and so that is going to make it more difficult than the previous ones. I would like to start by making a little sketch. It's not that difficult because it is a polynomial that was given to me in factored form. So all I really need to do is to mark where the zeros of the function are, which are -4, -2, 0, and 3. There's also this negative sign in the front here, which means that I'm expecting the thing to go to -infinity after all of the zeros. And here it's going to be going up and down. But because this distance is bigger than the other distances, then the function is also going to be going up a little bit higher in there than in the other spaces, which is just a thing about how polynomials work. And now, before I sketch the line that is tangent to that thing in two different places, I want you to visualize where you think I'm going to put it. There it is. It is tangent to my function at 2 points, which I am going to label as P and Q. Now, don't get me wrong, I'm not trying to tell you that you should consider this problem easy. I do know that it's difficult, but I want you to reach the end of the video feeling that you are able to solve it, even though it's difficult. However, there are two specific reactions at this point that I can't really understand how some people can have. The first one is saying, oh, then P has to be -3 because it's the midpoint between -2 and -4. How would that be a possibility in a difficult problem, that the answer would be reduced to, oh, it's just the midpoint? What possible reason would you have to say that the tangent point is going to be exactly in the middle of the two zeros? It doesn't even make any sense. A zero is a zero. A tangent is about derivative. They're not the same thing. And the second one is when people say, oh, so P and Q are going to be the local maximum of the function. Guys, this one makes even less sense. This one is not even just reducing the problem to something that is too simple to be true. This is just plain wrong. Turning points have horizontal tangent lines. This line is not horizontal, but it is tangent. Therefore, it makes no sense to say that P and Q would be the turning points, because they're not. Okay, so I've already expanded all of the products in my function because that's boring. You don't want to see me do that. And now I am going to take the derivative of that using my power rule. That's the derivative. And what I immediately want to do with it is that P and Q have the same tangent line. Therefore, the line has the same slope as itself, and therefore the derivative of the function at P and at Q must be the same. So that is one of the things that I want to write down. I'm going to go one more step and just plug in P and Q here, but it's going to look ugly. The 24s are not showing up because they were 24 here and 24 there. They have canceled out. So that is a very ugly looking equation. And this is made even more ugly by the fact that we want to find the values of the two numbers P and Q, but this is just one equation. So that's usually not enough information. When we want to find two values, we tend to need two pieces of information. But like I said before, there is one thing that we are forgetting here. Having the same slope only means that the tangent lines are parallel to each other. And in this problem, we know more. We know that it's actually the same line. Which brings me to the third comment that oversimplifies things, that sometimes people make this comment, oh, then you also need to write down that f of p equals to f of q. Well, no, can't you see that they're different? F of p is down here. F of q is up there. They're not the same. I know that this happened in the previous exercise, But that was because we were doing tangents at the same point. So yeah, f of one was equal to g of the other, but that doesn't mean that p and q are at the same height here. They're clearly not. What we do need to write down is that the tangent line at one of them passes through the other, or vice versa. It's going to be the same information, so it doesn't matter. So you want to write the full equation of one of these lines, not just talk about its slope like I have behind me here. And I know that in all of the other exercises, I have been doing tangent lines in slope-intercept form because that is the one that I feel most people are comfortable with. But there are not that many concrete numbers in this situation. There's a lot of letters, so I'm going to switch to working with point slope form now because that's going to be more convenient. So the point slope form of a line is that y equals the y0 of a given point that you know, plus the slope times x minus x0, which is the x of that same special point that you know. I'm going to do it at point P. So the slope is going to be f prime of P. And the special point that I'm talking about is exactly this one. The x coordinate is P and the y coordinate is f of P. So I'm going to put P here in x0, and over there in y0 I'm going to put f of P. That is the tangent line to this function at that point. And now the information that I have is that this line passes through that other point, which has coordinates q and f of q. So I'm going to substitute that here into the y and x of the line. There is another way that you can look at that as well. If you make f prime p the subject of that equation, you're going to find this, which looks a lot like slope of a line. It's rise over run, which we are seeing in the orange triangle that I just put over there. But I don't want to work with it in this way because of the division. I want to keep it in this way because then this still looks like a polynomial equation in the variables p and q. I know that we are not seeing the polynomials because we haven't substituted f of q, f of p, and f prime of p, but then if we did, that's what we would find, a polynomial equation in p and q, together with this other polynomial equation in p and q that we already had, that is two equations for finding two values, p and q. So that makes sense. It's just not a calculation that we are completely going to do because they have become huge, unmanageable polynomial equations. But like I said, this problem was meant as a technology assisted problem. We were not supposed to go any farther than this. Okay, so now I'm going to show you how I can use technology to finish solving that problem, because even that is not straightforward, is it? It's a system of two equations in two variables, but it's not two linear equations. By the way, if it was, I wouldn't even need technology to do that because I know how to do it by hand. But still, I keep saying that we should be able to solve it because it is a system of two equations and two variables. But why am I even saying that if I don't know how to solve it by hand because the equations are too complicated? Then what do I mean by it should be solvable? Well, what I have in mind when I say that is that every time you have one equation involving two variables, that can be represented by a curve in the coordinate plane. In this very simple example, the curve is a line, but you know that it doesn't have to be a line, it can be a curve. And it doesn't even have to be a function like these two examples. I'm pretty sure this one is still a function, but I didn't type it as a function. As you can see, it's x squared equals y cubed plus 1. So it's not what you're used to thinking of as a function. It is, though, an equation in two variables, x and y, and it has a curve in the coordinate plane. This one is not a function, though. Look at this red curve. X squared plus 2xy equals y cubed. So what I'm trying to illustrate, this curve has nothing to do with our problem, but it's that any equation in two variables is represented by a one-dimensional curve in the coordinate plane. So if you have two of them, you should expect that when they cross, and they will probably cross at some point, that will be the solution to both of the equations at the same time. So with that in mind, I have typed here f of x is the function that we were working with in the problem. And this light gray one is just the function divided by 10. So I did a vertical stretch so that it fits in the window. For what I'm going to do next, I don't really want to stretch the axis. So I am going to hide the function and just keep this shadow of what it looks like so that we can still look at it, but we're not really going to use it. What we are really going to use is this. Remember that this is the derivative of the function that we are trying to put a tangent line on. So I wrote my first equation here. Just the derivative of x is equal to the derivative of y. And I'm having to use x and y here instead of p and q for the names of the points like I was doing on the board, just because if I use p and q, then he's not going to draw it. So right now, please keep in mind that x and y are not independent variable and dependent variable anymore, but x and y are instead the names of the points where that tangent line is going to be touching our function. So as we discussed, the derivatives of both points need to be the same. So derivative in x is equal to derivative in y. And the picture looks incredible. I know that it looks like we are seeing two different things here, a straight line and then this oval thing, but it's only one equation, okay? The set of points in the coordinate plane that satisfy the equation that I typed has these two distinct parts. The straight line shouldn't be surprising because it is the line y equals x. And of course, if you're talking about one point and itself, then its derivative is the same as its own derivative. So all of the points in the line y equals x do satisfy that equation. But the interesting solutions are not going to be those because I want two distinct points. So the interesting things are going to happen along the oval thing. And the second equation that we had, which was the more complicated one, was this purple picture here. This is the one that says that the tangent line at one of the points actually also passes through the other point, okay? And I'm going to hide the function here because there's too much on the screen. So, like I was saying, each of these colors represents the points that satisfy one of the equations. And if I want to find the point that satisfies both equations at the same time, then what I'm looking for is the intersection of the two curves. So I'm looking for this point here or that point over there. Those are symmetric to each other. It's just that I didn't write anything in the equations that represents that one has to be on the left and the other has to be on the right. So if you switch them around, that's also a solution. So it's also not surprising that we are finding two solutions. There are also 2 points here and here that look like they are going to be something interesting, but they are really not what we are looking for because that's also on the line y equals x. So it's not 2 points and we want 2 points. The solution that we're going to take is this one. I hope that GeoGebra is able to give me the coordinates of the points. Sometimes with curves that are too complicated like this, he doesn't work very well, but let's try the intersection between this and this. Oh, there you go. It worked. It's point A, which is minus 3.34 and 1.84 that I'm reading on the left here. He also chose to mark B, which is the point that I was saying looks interesting, but it's actually not. He also marked some points C, D, and E for reasons that I really don't understand, because even if I hide the first equation, the purple one doesn't look to be passing through there. And he also didn't mark the reflection of A on the other side as an interesting point. So anyway, what I'm saying is that GeoGebra is very good, but this problem is kind of too complicated for him. So we got lucky that he gave us the coordinates of A. He could have been unable to do that. That is not to say that the problem is too difficult to be solved even with technology, okay? That is just to say that this particular technology may not be good enough if you're trying to do this with other functions. The important thing that I was trying to talk to you about was the structure of how you go about solving a problem like this one, and I think we're done. Oh, and I almost forgot to mention that problem 5 had a second part. After we have already found all the numbers and now we know that these are the functions, he also asks you to find a second line besides this line y equals 2 minus x. There is one more line that is tangent to both of these functions. So see if you can figure out what it is using a lot of the same tools that we have used throughout all of the other problems in this video, and just let me know in the comments the equation of the other line that you can find here.